Hello? Good morning, everyone. It's time to start. Okay, so in the last lecture, we introduced the general setting of supervised learning. As we mentioned before, supervised learning is the most important framework we're going to discuss throughout this semester. It provides all kinds of fundamental techniques about learning. So we know that to conduct supervised learning, you need to know what is the instance space, right? Instance space consists of all the examples or instances you want to make predictions, like news articles, where the task is to classify the articles, weather prediction, where the task predict the weather conditions. You know, that would be the instance space will be just the representation of the weathers. And then we need to define the label space, which is determined by the task itself. Right? For example, if you're doing binary classification, and then the label space just consists of two labels. If you're doing multi-class classification, you have a set of discrete labels. But if you're doing regression, meaning that you're predicting continuous label for your data, like you want to predict the stock price, you want to predict the temperature, then your label space is continuous, right? You actually have an infinite number of the labels in your label space. That's totally determined by the nature of the task. And then the key assumption is that we assume there's a mapping from instance space to the label space. So we can assume this mapping is a ground truth function, which can give any instance in the instance space a label, right? That is the ground truth label. So the goal of supervised learning is to find out this ground truth function, find out a good approximation to this good function. Right? How do we conduct that? We need to prepare training examples, right? Training examples are pairs of the instances and the labels given by the ground truths. We hope that by giving a finite set of training examples and their labels, we're able to find a good approximation to the ground truth function, or ground truth labeling function. Okay, that's supervised learning. Of course, if you are training data, you don't want to provide any labels, then it is called unsupervised learning. If your training data consists of both labeled training examples and unlabeled training examples, this is called semi-supervised learning. So, and then we briefly introduce the definition of decision trees. Right? This is a decision tree is the very first supervised learning algorithm we're going to focus in this semester. The reason is not because it's not only because it's simple and intuitive, but also it gives a good connection between the way of human thinking and the way we create classifiers from data. So what are decision trees? Right? So actually we briefly mentioned in the last lecture, but here I want to read through this again, right, to reinforce your idea of decision trees. So basically, decision tree in general is a hierarchical structure that represents the data, the divide and conquer strategy. Right? Divide and conquer is mainly reflected in the creating process of the decision trees. So each node in the tree represents a subset of data. So starting from root node, obviously root node will represent the whole data set. And then when it grows new branches and add new intermediate nodes, the data sets are partitioned into smaller and smaller subsets. And each node is associated with a small subset and simultaneously associated with the test feature. So why do we associate test feature with each node? Because we're going to use that feature to further partition the data sets to grow new branches and new child nodes until we reach the leaves of the trees. So what is a leaf node? So in most of the cases, leaf node just indicates a subset of examples who share the same label, meaning that all the examples in this subset, they have the same label. And in that case, it is unnecessary to further split data set. They'll just stop here. Then we give a label of this leaf, right? Just the label of all the examples in the corresponding subset. So that's the general definition of the decision trees. So the learning of the decision tree essentially is to recursively create such a tree to represent your training set. And that's it. And we're going to discuss the classical learning algorithm to create this decision tree, which is called ID3. But before that, I mean, to reinforce the concept or the definition of decision trees, we're going to first manually create a decision tree from scratch. Okay. So here are our data sets. So you can see that it's just a collection of the colored shapes. So those shapes are labeled into 3 categories, right? A and B and C, right? So please take 1 second to look at those examples, right? Before we start creating our decision tree. Let's think about, right? Just use your intuition, right? Suppose I give you a test example, which is a red triangle, right? According to the data, which label do you believe is for the red triangle? Any thought? Just a guess.
B. I guess B.
Why?
Because it's the only one with red or triangles.
Okay, are there any suggestions?
I think it would be unlabeled, right? There are no red triangles in that diagram.
Yeah. I think your suggestions are all perfect. Yeah, intuitively we should predict red triangle to be class B or label B. Right? Why? Because from our observation, all the red shapes, no matter what kind of type of shape they are, they're all labeled as B in the training set. So we believe that given a new red shape, it should be labeled as B. Yeah, and that's right. I mean, if you build a decision tree classifier, it's actually even more general. If you build any other classifiers, then most cases you're going to predict this red triangle to be label B. So now let us manually construct decision tree and to verify our guess or intuition. Okay, so as we just mentioned, right, decision tree is a way to hierarchically partition the data, right? So how can we partition data? Or partition examples, we need to depend on the attributes, right, or the features. So what kind of attributes do our training examples have? Or what kind of attributes or what kind of features that describe each training example? And yeah, this is one. This is actually a type of shape, right? And what is there any other attribute?
Color.
Yeah, color, right? So actually we have 2 attributes that describe each particular example, right? So one is color, one is shape. Right? So theoretically speaking, to construct tree, we can use whatever attribute to start to partition the data. Right? So let us just use color attribute to partition those examples first, and then use shape. Right? So how many colors do we have for this data set? 3, right? And red, blue, and green, right? So accordingly, we're gonna partition the training data into 3 subsets. Right? Each subset contains the examples sharing the same color, right? Blue, red, and green. So we can view this subset as all the blue shapes, the subset in the middle, all the red shapes, and the subset on the right, all the green shapes, right? So we can first take a look at all the red shapes. As we just observed, right? All the red shapes, no matter what kind of type of the shape, they are all labeled as B. Meaning that all the examples, this subset, share the same label. So it's unnecessary to further partition this subset. It's not meaningful. So we're going to stop and then create a leaf node represents this red shapes. And because all the red shapes have the same label B, so we're going to mark the label of this leaf node as B. Okay? And then let us switch to the blue shapes, right? The very first subset, right? So do blue shapes share the same label?
No.
No, right? So actually, the labels in the blue shapes are quite diverse, right? We have a label C, we have label B, and we have label A, right? So that means we need to further partition the blue shapes according to type of shape, right? Because we have already used the color, right? All the subset here, they have the same color. It's not possible to use color again to partition data because all the examples share the same color, right? So the remaining attribute that can be used to partition, to further partition this subset is the type of shape. Right? So actually, we have three types of the shapes: triangle, square, and circle. Accordingly, we can partition the blue shapes into the three even smaller subsets. So now let us look at the corresponding subset. So the very first subset are all blue triangles. Do they share the same label? Yeah, right? All the blue triangles are here, right? So they share the same label, meaning that they their labels achieve the best purity. There's no need to do the further partition. We stop here. We create a leaf node and then mark the label of the leaf node as the label shared by all the examples, right? Here's B. And similarly, we can take a look at blue squares, the second subset, right? All the blue squares are here, right? There's actually only one blue square labeled as A, so they share the same label. So of course, it's not feasible to do the third partition, right? So we create a leaf node and then give the label of leaf node A. Okay? And the third subset are blue circles, which are here, right? So we know that all the blue circles have the same label, C. So it's not necessary to do the further partition. We stop here and then assign the label of this leaf node as C. Right? So now we finished the drawing of the branches and nodes along this way, right? And in the middle, it has already stopped. The remaining is the right branch, right? The green shapes, right? So do the green shapes share the same label? No, right? It's obvious now. They actually can be labeled as B or labeled as A, right? So we need to further partition the green shapes according to the type of the shape. So in the data, we have two different shape types, square and circle. And so now we can see that the green circles, they have the same label, A, right? So we stop moving and we create the leaf node with the, and assign this leaf node a label A, right? Similarly, for green squares, they all share the same label, right? They both share the same label actually, and label B, so we create the leaf node with label B. So now we have finished the construction of this decision tree. Right. So it's That's a very good question. We're going to discuss in a minute. Uh-huh.
So what if we have like some color that's not in this like first level, so like black circle?
Yeah, you're right. I think your question is very similar to Tim. We're going to discuss about this in a minute. But I mean, from just this naive or intuitive procedure, I think everybody will be comfortable with that, right? This tree. So and through this construction, we can understand the idea of decision tree, right? It's a hierarchical representation of the data, and the higher level the node, the larger the subset of data it represents, right? So the root node represents the whole data, and then each node is associated with a feature. Why? Because we're going to use this feature to further partition the data set associated with this node, right? The root node, we use color feature to partition the data, and we have 3 different colors, so we can partition the data into 3 subsets, right? And then we do the further partition if the labels are subsets are mixed. So now, given this decision tree, does anyone have a clue like how to do the prediction? Right? Suppose I will give you a new color sheet. How do you make a decision? How do you make a prediction of the label by using this tree?
So what if we classify this tree as lost in the same order?
That's a question. That's actually the problem that we need to make a rule, right? How to make a prediction. And we need to ensure that the prediction only gives you one label, not multiple labels. Any thought?
You could just follow the same logic, right? So if it's like, for example, like if it's the green, like triangle or something, you could just say, oh, it's green, put under the shape, and then like instead of like coming to a decision, you say, oh, it's green, so there needs to be a new leaf, and then you just say, okay, green triangle, and then you put it there.
Yes, exactly. Right. So,
Not a question, but an observation. I was making the decision tree where the shape is first and color is second. And if you go to the square one first and color is second, then they're both red and green squares, and both of them are labeled B. So how would how does that?
oh yeah, I mean that relates to how do you construct the tree, right? But let us just assume, which we will get into that topic later. But let us just assume, okay, you have a tree. You are given a tree. How do you use that tree to make a prediction for new examples? So actually, just like you said, right, we can just start from the node, root node, and look at the feature, and then look at the testing branch, right? So you just follow the branches of those trees and test the feature value if obeys the corresponding branch, and move to the next node. And if you can find a path from the root node to some leaf node, you just record the label on the leaf node as your prediction.
I guess it's more of a follow-up question. What if like you're wrong? Like what if like when you go to like verify a prediction, there's like another, for example, like you say like the green triangles go there, then you have like something that doesn't confirm that. Do you know what I mean?
Well, I think your problem has two. I mean, there are 2 points in your problem. First, what if your tree is not complete? Right? You cannot find any path. And second, what if you have 2 trees? This is what he just mentioned. They might have inconsistent predictions. Well, yeah, that's a problem. But it's possible that you have 2 structurally different trees and use them to predict the same example, but end up with different labels. It is possible. prediction using a given decision tree is pretty straightforward. You just start from a root node and look at test feature, and then take the branch which is consistent with your example. What's wrong? So, and then you do the same thing on the second node, and then go through and find a branch that matches your example, and until you reach the leaf node, then you use the label on the leaf node to make the prediction. That's it. So take the, sorry. If you look at our previous example, red triangle, right? So if you want to make a prediction on the red triangle, we first look at the root node, which where the test feature is colored. So we say, okay, along this branch, it is consistent with the red triangle, right? Because the color is red. And then we arrive this node, and we found out, okay, we have already arrived at the leaf node. Then there's no need to do the further testing. We just stop here and report the label B. That's our prediction. So you can see that this label B is consistent with our intuition, right? So, but there's a problem. Before we get to that, any question regarding the prediction rule with decision tree? I think it's pretty intuitive, right?
Is there any advantage like starting with the color and say or say after a color? So is there any like advantage or disadvantage of doing?
I think you're still talking about which order of the features are used to partition the data, right? We'll get to that problem very soon, like after 5 minutes, 10 minutes. Okay. Any other question regarding? Hi.
Yeah, our example, we had 2 attributes and we ended up with 2 layers. Is that true in general?
Yeah.
If there's any attributes?
Yeah. Because after using one feature to do the partition, we're gonna kick it out from the candidate attributes. Why? Because all the subsets will share the same attribute value, so it cannot be used again to partition the examples. So we need to kick it out from the attribute set and select one attribute from the remaining set to do the further partition, so that one level always corresponds to one using one attribute. Any other question regarding our definition of prediction rule using decision trees? Okay, so now let's talk about the problem, right? And thanks to your observation, and you have observed the problem, right? So let us look at another example, which is the green triangle. Right? So if we apply this rule, what can we find? Right? What is the problem can we find? So first we test the color attribute on the root node, because it's a green triangle, it follows this branch, right? And then we come to this node, and then we test the shape attribute, right? And but we found out the shape type is a triangle, which doesn't match any of the existing branches. That's a problem, right? That means I cannot give you a label for this green triangle, right? And that actually make your decision tree much less useful, right? Because I want to give you a label in whatever cases. So the problem of the manually constructed tree we did a minute ago is that the tree is not complete. It cannot guarantee it can give a prediction for every possible past example. So to address that problem, intuitively we should create an actual branch for this, and which gives at least give a reasonable label on that. Although this green triangle does not appear how can we give a label for that? We're going to talk about that question later, right, when we discuss the decision tree learning algorithm. Okay. Now, to finish our introduction of the decision tree representation or definition, we need to look at another representation of decision trees. So if you're given a decision tree, we know that make a prediction is equal to finding a path from a root node to a leaf node. So each path, it actually represents a root. Okay? So suppose you're predicting the label for a blue triangle, right? So you can see the path it goes through just tells you if the color is blue, and if the triangle, if the shape type is triangle, then predict with the label B, right? And if for this path, right, if the color is green and the type of shape is square, then predict with label B, right? So you can see that every path from the root to a leaf is a root. And if you just enumerate all possible paths from the tree, those are all possible rules can be used to make predictions. So the full tree is equivalent to the conjunction of all the rules. So this is another popular representation of decision trees, although it looks much more boring. Right? So it's not as fancy as this tree, but these are very easy to be dealt with computer programs. Right? So you can actually represent trees as the first order logic predicate. Right? It's just a conjunction of rules. But those two representations are the same. So, and from our example, we see that the outputs of the decision trees, namely the labels, are discrete, right? And our many construction are making such kind of assumption as well, right? But that does not mean decision tree cannot do regression, meaning that your label is continuous. But how can we do that? So because the label is continuous, that means we cannot assume that the examples in a leaf node share exactly the same label, right? Because it could be 0.2, 0.1, 0.13, they're all continuous, right? So we need some new stopping criteria to create the leaf node. At the same time, suppose we have got the leaf node and we have a subset of examples, and usually we're gonna hit average of the continuous labels in the subset as the label for this leaf node. Does it make sense? So, and of course, creating decision trees, we need to, in practice, we have noisy data, and also we need to control the size of tree and to make it not that large, right? Which we're going to discuss later. So, and also the examples just uses the instance we discussed just uses categorical features, right? But in practice, there are many numerical features. Like for example, we can use length as your feature or attribute. You can use height. You can use temperature, right? So when we create decision tree, how can we deal with numerical attributes? The strategy is to discretize them. It's very straightforward. It's just binning, discretizing, or thresholding, whatever. In this way, you're gonna convert a numerical feature into a categorical one or binary one. Right? So for example, all the examples here, they are represented by two continuous or numerical features, x and y, right? So of course, we still want to build up this decision tree from this data. So how can we do that? We're going to first adding several thresholds on the two features. So for x, it's be 1 and 3. For y feature, it's 5 and 7. thresholding means that I will have a binary feature. If x is less than 1, is 1. If x is bigger than 1, is 0, right? If x is less than 3, the binary feature is 1, right? If x is bigger than 3, the binary feature is 0, right? And then we have like 4 binary features to re-represent those examples upon which we build a tree, right? So this is the tree. So you can see that each the features associated with each node are just binary feature from some threshold. So if I take a look, say this example, right? So this example, when we make a prediction, suppose I have a corresponding neighborhood, right, like here. The example stay here, right? So first, it will test if x is less than 3. We know it is false, right? So we're gonna go through this way, right? Because x is bigger than 3. And then we'll test if y is bigger than 7, right? And because our test example is here, right? Of course, the y feature is not bigger than 7, less than bigger than 7, so it's no. And then it reaches leaf node, which is labeled empty.
What do you do about boundary values like something like x equals 3 for that person too?
What is the boundary value?
Yeah.
Oh, that's a good question. So the boundary value are either included into less than or bigger than. That depends on how you define the thresholding function. I can use x less than or equal to 3, or y bigger than 7, or y less than 5. So you can include them in either infinity, like less than or equal to this, or bigger than or equal to that.
Why is the x attribute in the third layer? It's in both in the first and the third layer. Shouldn't that be only in one layer, the x attribute?
Which one?
The x attribute. It's in the first and the third layer, right?
Yeah, yeah. But this actually represents 2 features, 2 attributes. You see, this attribute is actually a binary attribute, if x is less than 3 or not. And this is actually another attribute, x less than 1 or not.
Oh, so these are.
Yeah, they are treating as 2 attributes. Don't view them as 1 attribute.
Gotcha.
Okay, hopefully this is everyone's comfortable with this, right? Okay, so although decision tree looks intuitive and simple, but actually it's not simple. It can represent quite complex classifiers, meaning that they can be nonlinear. They can represent nonlinear relationships between the labels and training samples. How can we see that? If we look at the decision boundary, right? Decision boundary is the boundary which separates all the positive examples from the negative examples. You can see that this boundary can be quite nonlinear. That means decision trees are quite expressive, and they're more expressive than linear models, which are widely used. And we'll discuss linear models like linear regression, linear classifiers later. But just to let you know, decision trees are quite expressive. They're typically nonlinear classifiers, nonlinear regressors. Okay. To summarize, decision tree is a compact data representation, and it's pretty natural and intuitive because it's analogous to how humans summarize things or think of things, right? You can use some survey as analogy, right? So if you want to create a survey, how do you design problems? It usually has some kind of a hierarchical structure. And predicting with decision tree is pretty simple and easy. Why? Because we just from the rule node and test the features and find a matching branch and do this again and again until we arrive at some leaf node.
What is 20 questions?
Yeah, that's about survey question. So if you want to make a survey, right, how do you make them? So people usually make the questions in terms of a kind of hierarchical structure rather than just list a flat list of current questions. Okay, then we can talk about, we can think of this last question, right? Actually, many of you have pointed out this issue, right? So even from a manual constructing experience, we know that given the data, there can be many ways to construct the trees, right? Why? Because there are many orders of the attributes can be used, right? You can first use color and then shape, or you can first use shape and color, and this will end up with different trees. And then a natural problem will be like, what kind of order for these attributes will be the best, or will be the practically good choice. This is also a problem we need to address when we develop a learning algorithm to learn decision tree from data. Okay, so these are about the definition of decision trees, and after this class, I recommend everyone to manually create another tree by following the shape and color order, and then you can contrast the structures of two trees, and also verify if for every test example they end up with the same prediction, but it's unlikely. Okay, any questions regarding definition of the decision trees and also the rules for prediction? Everyone's comfortable with that? Great. Why is that? Okay, so next we talk about how to learn decision tree from data, right? So given the definition, right? So we're gonna discuss the classical ID3 algorithm to learn a decision tree from data, which is essentially to construct a decision tree to represent data. And you will see that the ID3 algorithm essentially is a greedy heuristic. And why we have to choose a greedy heuristic to create a tree rather than choose some globally optimal tree we're going to discuss. So this is just the appetizer before we talk about the algorithm details. Just to share the brief history of decision trees and tell you how old this technique is. It's being developed a long time ago, and starting from 1960s, and first proposed by psychologists because they first found the similarity. They first found the kind of like tree structure and heuristic searching procedure of human decision process. And then in the late 1970s, Finland, he's the pioneer of artificial intelligence, one pioneer. He developed ID3 algorithm using the so-called information gain to learn decision tree from examples. And expert system is a buzzword in that time. It's a kind of like machine learning or artificial intelligence nowadays. So, but they are referring to the same thing. They're just referring to some machine learning model. And then later, the statisticians they develop a card trick, another type of widely used decision trees for both classification and regression tasks. So that's why I mentioned that you can do the regression using decision trees as well. And in the 1980s, there are a variety of the improvement over the existing tree learning algorithms, mainly dealing with data noises, how to discretize continuous attributes, and how to deal with missing data, etc. And also how to do the pruning of the trees. We see that you cannot let your tree to grow too large. That will bring the risk of overfitting. And then in 1990s, Finland updated its algorithm, so it has two classical versions, or you can see it as enhanced version of ID3. One is C4.5, one is C5. C5 is commercial version. Right? So that means their source code is not released. But I used C5 before, it works really well. And then further, I mean, in 1990s, people find ensemble learning is really, really powerful and helpful. And the development of ensemble learning techniques can be viewed as a small revolution in the machine learning area. And people find that, okay, if you do the backend boosting to ensemble learning strategies over small decision trees, their performance is dramatically better. So actually, boosting and backend are commonly used in nowadays machine learning libraries and package and applications. Those are a brief history of decision tree research. So we're going to use some concrete example to show how the decision tree learning algorithm works, meaning that we're going to look at those training data and look at algorithm steps, and then we'll execute those algorithm steps on this piece of data to create the tree so that we can better understand the algorithm details. So the example here is a decision task. That is, I want to predict or want to decide whether I'm gonna play tennis today or not, according to the weather conditions. So the weather conditions are represented by 4 attributes. So one is the outlook attribute. It might take sun, overcast, or rain. Right? And the second attribute I'm going to use is temperature. Of course, it's discretized temperature. It has 3 levels: hot, mild, and cool. And the third feature is humidity, 3 levels: high, normal, low. And the fourth feature is wind, right? Whether it is strong. It has strong wind, it's very windy, or weak. Okay? So of course, we're doing the binary classification, so our label are either positive or negative. So we have collected 14 examples, right, in the past 2 weeks. So so you can see these numbers are in those rows index those examples, and each row is one particular example. And for brevity, we just use the capital of the first letter to indicate the feature name and feature value. For example, the very first row means that, okay, in the first example, the outlook is sunny, and the temperature is hot, and humidity is high, and wind is strong. So my decision was to stay at home, not play tennis outside. Okay? And for this example, 7th example, the outlook is overcast, and the temperature is cool, and humidity is normal, and windy is strong. My decision is still to play tennis. Okay? So it's positive. So here is the decision tree. Our ID3 algorithm will learn from this data. Okay. So what is ID3 algorithm? What does ID3 algorithm do, right? So it essentially performs a recursive procedure to build the decision tree in a top-down fashion, meaning that we start with the if node and look at the associated whole data set and find a feature to partition the data, right? And create new branches and new subsets, and then call itself. That's why it's called recursion. Call itself to look for other nodes, other features to split data, create new branches, and then get new subsets, and call itself until it reaches the leaf node or stop. This is the general idea. So now let us get to the detail. This is decision tree algorithm ID3. So we know that to do this, we need the input consists of 3 type of inputs, right? So first, S is a set of examples which are associated with current node, right? And label, of course, are the labels or target attributes of prediction for those examples, input example S. And then attributes is the set of attributes that can be used to split the data. So as I just mentioned, ID3 will recursively call itself to partition the data, create new branches and nodes. So this is like a tree construction, tree traversal algorithm framework. So I assume everyone at least have heard of that. Yeah. So now, if you were the author of ID3, you're gonna develop a recursive algorithm to construct such a tree. What is the very first thing you need to consider to design a recursive algorithm? Any thought?
What's the base case?
What do you mean by base case?
Like when are you done?
Yes, exactly, right? So that's a very important. Whenever you write a recursive program, you need to know when you stop, right? So we know that the recursion in computer program is done by stop, right? So you call itself, you move the stack pointer to one to upward, right? If you keep call itself, you're gonna exhausting the stack resource, right? So if you don't stop at right time, at some point you just exhaust all the stack resource and you're gonna crash. Right? So that's a common thing error. We will develop a recursive algorithm, and the system will just throw out an exception or error message saying that your stack is overflow, right? So but anyway, we do not need to drill down to the details of operating system. But this is a very, very important principle. Whenever you design a recursive algorithm, you need to consider when this recursive call should end, or when to stop. That is called that is called stopping criterion, right? So now, suppose you're giving this current set of examples and attributes from which you can split for the split S, right? Also all the labels for the examples in S, right? And when do you think we do not need to do the split and the return leaf node? And then you?
If all your labels are the same, or if you're out of attributes.
Yes, exactly, right? So first, this is actually reflecting our manual construction experience. First, if all the labels in S are the same, it's unnecessary to split the data set anymore, right? We just stop here. We should create a leaf node and say and put this unique label as the label of the leaf node, right? But the other thing worth your notice is that if your attribute set is empty, you have to stop as well, right? And don't consider this impossible. Actually, it's quite common. Imagine that you have a very large set of examples, like you have 1 million examples, but you will have 3 features. It's very unlikely that you can only partition this data 3 times, and then you end up with all the examples being sharing the same label, right? So it's possible that you have used up all the attributes, meaning that this set is empty. You still have mixed labels in your set. And then what should we do? We have no choice, right? We have to create a leaf node, and then we assign a label. But to be safe, we're gonna use the most common label in S as our leaf nodes label, right? Any question regarding this base case or stopping case? When should we stop calling itself to create new branches nodes. Yeah, I want to emphasize this case because if you don't consider this part of the case, it's likely that your algorithm is just running forever. And with black screen, you don't know why. And the very first case, I mean, if all examples share the same label, it's pretty intuitive, right? And when all the examples they're uniquely labeled, okay, we should stop and create leaf node, right? But be sure to look at, to test if your attributes are empty. If your attributes haven't been used up, you should stop as well. Okay, so if the stopping cases are stopping conditions are not met, that means we can call itself, right, to create new nodes or new branches. How should we do that? Otherwise, right? So we're gonna first create a root node for the tree. Here, root node does not mean like the whole root node. It just means the root node for the current subtree, where we're gonna grow new branches and nodes. And then we're gonna look at the attribute in this attribute set. Right? We're gonna find out an attribute A, which can best split current data set S. But the problem is, what do you mean by best split S? Going back to our previous example, what do you mean by selecting color or shape type? Right? Which one do you think is best? Can best split S? Right? That's a problem we're going to discuss later. But here we just want to assume that, okay, you know that I have some kind of mechanism. I can rank the attributes in this set to find the best one. And this attribute we call A, right? And then we're going to use this attribute A, to split our data set S. How can we do that? We just look at every possible value V of that A can take. And for each possible attribute value V, we just create a new tree branch. Right? This branch is associated with the testing condition, whether attribute A equals to V, right? And then we look at all the examples in S whose feature A takes value V. Right? We denote this subset example as V. Right? So now it comes to the critical point. So if SV is empty, what should we do? Right? It corresponds to the green triangle case, right? We just mentioned. We found out, okay, for a particular attribute value V, right, actually current data set does not contain any examples taking attribute A to be value V. What should we do? Should we just delete this branch? No. Yeah, all right. So we cannot delete the branch. If we delete the branch, we will have the same issue as our manually constructed tree, right? Remember the green triangle things, we cannot find a matching branch. We're stuck there, we cannot provide any prediction. Right? That's not acceptable in practice. So we still need to preserve this branch, but for this empty subset, for safety, we create a leaf node, and then with the most common value of the label, yes. So this says, okay, because I don't have any examples, take this feature A to be B, then I give the most common label in S itself as my prediction. So if we go back to look at the tree we just manually constructed, right? So we know that when we partition examples according to the color, all the green shapes, we don't have green triangles. So our previous strategy is just ignore this branch. That brings some problem. Now, in our ID3 algorithm, we're going to construct a branch. But for this leaf node, we just pick up the most common label in the data set associated with this node. green shapes, right? Of course, they are high scale because we have two label B examples and two label A examples. And in this case, you can choose whichever label you believe. That's why we should do this, right? Because we want to generalize at test time. We need to cover all possible test cases to avoid the failure of making a prediction. Any question regarding this step? Mm-hmm. How do we? Oh yeah, that's a good question. You can just look at how many examples for each label. You just pick up the label who has the largest examples. But there is a chance to have ties, meaning that okay, the two labels they have the same number of examples. Then, I mean, in this case, you can choose whichever you believe, or you can add a bit your own preference on that. Why I shouldn't say it doesn't make any difference. I mean, practical choices are like that. If you believe, okay, in that case, either one is fine, is okay. If you believe, okay, my own knowledge, my domain knowledge tells me, okay, this is one, this is more likely, then I choose that.
So the rule number 3 is that each possible value. So we should have like attribute values to be finite, right?
Yes.
For example, here color.
Yes. Yes, exactly. We need to assume the attributes to be finite, mean that their category, they have they actually is a set of discrete values. That's why we talked about how to deal with numerical values. Right? We cannot deal with numerical values because we cannot create like infinite number of branches. We need to first discretize them.
I mean, if you want to make it like even buckets, so they need to be like finite. So like for color, so as I said, we need to make it discrete.
Can I say it again?
So like I'm just admitting what you say. So say that like so even for the color, if we make multiple buckets, but those buckets should be finite. I mean like being discretized is not the only thing necessary, but they should be finite.
Yeah. I mean, binning, you cannot discrete them into infinite number of beans. That's not feasible. Even you do binning, you have to ensure the number of beans is finite. Otherwise, you cannot practically create an infinite wide trees. Right? And that's why in many cases, in practice, people instead of using binning, people are using thresholding. To use threshold means that okay, I'm going to convert this numerical feature into a binary feature, less than 3 or bigger than 3. I can add multiple thresholds to convert it into multiple binary features. That is used more often. Any other question regarding to this step? Mm-hmm.
So it says add leaf node the most common value label in S.
Mm-hmm.
I was thinking it would be the most common value of the label in S for that node that you're leafing off of, rather than.
Yeah. I mean, this is one strategy. This is you can even use the most common value in the whole data set. It is okay. I mean, I just provide the most common choice. And as long as, in practice, you have many more choices. As long as you think that is better fitting your own problem. Like you can even like, I suppose, you can even make a more complex strategies like, okay, if the size of S is small, then I'm gonna go up one level to see its parent and look for the common values. And it can be as flexible as you want. Any other question? Okay, great. So now we have addressed all the corner cases, right? If SV is not empty, what does it mean? It means now we can safely call the algorithm itself to create new node and new branches, right? So how can we do that? We just below this branch and why? Because all SV, all the examples in SV, their A attribute have the same value, which is V, right? How do you use this A to partition the data set again, right? It's not possible. So that's why each recursive calling, we're gonna kick out the used attribute. And then the label, of course, will be all the labels in SV. And then you can imagine that, let me, I will just simulate how this algorithm is calling, right? So at the beginning, it just start from the root node, right? And create a set of branches and select attribute, say like A1, we create a set of branches, right? And then at this particular set, it call the algorithm again. Now using attributes, a new set of, using the new subsets, attribute labels again. So they create a new node, and then a set of new branch. And then it look at this particular subset, and suppose at this subset, the stopping condition has already been satisfied. That means, okay, I won't call myself again. Right? I stop here. I create a leaf node. I put a label, say label 1, positive, right? And now I return from my recursive procedure from computer programming perspective. I pop up my stack, right? And then look at this node and then go back to this level and then look at the subset here and recall the ID3 algorithm and to test if there's new nodes or branches should be created, right? If it happens that the stopping condition is met, and so we're gonna create a leaf node and then return, right? Similarly, we can do this and return. And finish this level and go back and look at this. Right? And look at this and call ID3 to partition the data set associated here. And suppose this time we still met the stopping condition, we create a leaf node and give another label, and then go back to this level and look at this subset and call itself. This is the whole procedure. And hopefully it can give you some sense how this algorithm is executed. But if you are familiar with the data structure, like trees and tree constructor and tree traversal, all kind of stuff, so they actually follow the same procedure. Does it make sense? Okay, so I want to emphasize two corner cases because this algorithm is really intuitive, I believe, for most of you, or for all of you. But just beware the two corner cases. First, if the attributes have already been emptied, stop and create leaf node. Second, if some subset along branch is empty, right, you still need to create a leaf node. But you can choose a reasonable strategy to assign a label on that leaf node. And only consider two cases will make your decision tree algorithm very robust when dealing with any kind of cases, because I've seen many situations in the past, and students complain that, okay, in this case it works well, in that case it just crashed. I don't know why. And we just forgot these two common cases. Okay? So, so the remaining, I guess, 5 minutes, so we need to, I just want to mention the only remaining question for implementing this algorithm. At each step, how to tweak the attribute split, right? And we previously mentioned that each time we assume that we can rank the attributes, right, and find the best one. Like what is the best one? The one we believe that can best split as, but we have never explained what you mean by best splits, right? So that leads to let us put aside the ID3 algorithm and consider like if you're powerful, you're the God, right? And you want to create decision tree from the data. And we know that depends on the order of the features used to split data. We can have many, many trees, right? So which tree do you believe is the best? Intuitive. Don't read the slides. Right? Tell me your guess, right? Which tree do you believe?
Can you repeat that question? Can you repeat that question?
I mean, we know that there are many, many trees can represent the same data, right? Equally well represent the same data. So those trees have varying structures and sizes, right? And which tree do you believe is the best?
So one way of thinking is like the height of the trees is like easier to find the solution. So like if you can like have like a more fan out at each level, that would be like faster to find the solution.
So you believe the shorter the tree is better, or the shallower the tree the better?
I mean, if you can do it, it's better. Like if the lower, I mean, like if you can decide your test with the fewest number of attributes, that would be the or prune it such a way that the height gets lower.
Okay. Any other thought?
Probably like the least complicated tree that still gives the correct results.
You mean the least complicated trees will give what?
The least complicated that will still yield like correct results, so you can like verify it's still correct.
Yeah. I mean, all your thoughts are really good, but this answer actually don't have the true answer. This is actually a belief. It's a choice. Like, why? There's no theory guarantee that you should choose the largest one, choose the smallest one, but there is some kind of a philosophical principle, which is called Occam's razor principle. So basically, here we're gonna obey the Occam's razor principle, meaning that we're gonna believe the smallest tree is the best. So what does it in general mean? And here I just want to refer to the Occam's razor principle. So it's telling us how do you do the model selection for any research problem, scientific problem, engineering problems. And people found practically this process is really useful and most widely used. So like, give you any observation, give you any problem, like we can develop a bunch of theories or models which can give an explanation. Right? Suppose you have 10 theories to explain why, what kind of example should I give? Right? Why the Earth is circling around, running around sun, right? You might have 10 theories, right? And why is orbit is like oval, right? You might have 10 theories. Right? And now the question is, which theory you're going to use, or which theory you're going to choose. And Occam's razor principle tells us we should choose the simplest one, with the least assumptions, with the least complications. The idea of Occam's razor principle is that without necessities, don't make your model more complex. So if we look at the decision trees, we might find like, okay, we can create a very large tree to represent data, and we can also create a very small tree to represent data. Then we believe the small tree is better, is more robust in unseen examples, in future examples. So now let us assume we believe such a tree is the best. And of course, I mean, we will have some mathematical justification of Occam's razor when we talk about computational learning theory. But now let us put it out, right? We just assume that we believe the smallest tree is the best, right? But how do we find the smallest tree? That's an issue. Why? Because if you want to find the globally smallest tree, you have to enumerate all possible order of the features to do the split, right? And that's a huge number. Right? Even for 10 features, you can imagine the number of permutations of these 10 features. Right? It's definitely huge. It's not feasible. That means in practice we'll never be able to find a globally smallest tree. And what should we do in practice?
Should pick the attribute that gives us the most number of leaf nodes.
Yes, yes. So, but I want to express it in a more general sense, meaning that we need to adopt a heuristic strategy. Right? And I need to make a trade-off between efficiency and the goodness, right? So I don't want to, I gave up the global optimum, right? And to gain sufficient efficiency. And each time I choose a heuristic principle, we know that it just satisfies the local optimum. Right? At current step, which kind of attribute can make my tree to be to have labels as pure as possible, right? And so that I believe, because each time I can find an attribute to split my data sets, so the improvement of the purity of the labels is the best. So I believe that only after a few steps, I can arrive at the leaf node, so I can stop. So overall, I get a small tree. Right? But that doesn't guarantee you're going to end up with the global, the really smallest tree among all possible trees. That's the key idea. The key strategy is to, in each step, select a feature to split data to be as pure as possible in terms of the labels. So I believe that in this way, we can reach the leaf nodes sooner than just randomly select the attribute. Right? So, and then we need a measurement to evaluate how splitting the data with this particular feature, the purity changes, right?